In this video, we will be solving the mystery of why our body uses more glycogen stores as we increase exercise intensity, as demonstrated in class by Van Lee.
In our model, we're going to be defining mass as ATP pool, and we're going to be defining our inflow as oxidative mechanisms, being fat and carbohydrate metabolism, and which switches to non-oxidative mechanisms, being glycogenolysis and the PCR system. We're also going to be defining our outflow as muscle utilization of ATP.
Alright, our hypothesis is that when exercise intensity increases, our muscle glycogen use goes up, just like we said in our problem. However, we believe that the reason we start using more muscle glycogen is because PDH is at a maximum activation, which causes our body to switch to non-oxidative methods of metabolism, such as PCR and glycogenolysis. Alright, so my British twin Elizabeth did a great job of explaining our hypotheses really quickly, but now we're going to go a little bit more in depth. So, normally when we're doing moderate intensity activity, we're using carbohydrate and fat oxidation to give our body the acetylcholine that it needs to further push it into metabolism. So in this case, PDH is really able to keep up with the flux of glycolysis. So we go from the acetylcholine that's produced here, we go on to the citric acid cycle, the electron transport chain, which turns all of the substrate into ATP for our body to use and to be used up by the muscle that most requires it. However, when we engage in really high intensity activity, we have a rapid increase in muscle utilization of ATP, which causes our ATP pool to decrease dramatically. ATP demand is really high, and that's why we think that our PDH isn't able to keep up, and this correlates exactly with what we stated in our hypothesis and what we saw in the Howlett study. Alright, so what are the consequences of PDH not being able to keep up with glycolytic flux? Well, in this case, we have an inability of our body to use the normal oxidative mechanisms that it used in moderate intensity activity because PDH isn't able to convert the pyruvate into acetylcholine. So we're using primarily glycogenolysis to provide our body with ATP. So it provides us with really quick sources of ATP to bring to our pool. Additionally, when muscle utilization increases, we also get a lot of ADP increase, which can combine with PCR to create ATP that also goes into our ATP pool.
The study we looked at to test our hypothesis was titled The Regulation of Skeletal Muscle Glycogen Phosphorylase and PDH During Maximal Intermittent Exercise. The study was conducted by Perlin et al. In 1999. This study looked at 6 males whose average height were 178 centimeters, the average weight was 85 kilograms, and the average age was 28 years. The participants of this study cycled at 100 RPM and completed 3 30-second bouts of exercise. There were 4 minutes of rest in between each bout, and muscle biopsies were taken at rest, 6 seconds, 15 seconds, and 30 seconds. The biopsies for this study tested the rate of ATP turnover from the PCR cycle, the rate of glycolysis via PDH, and the flux through PDHA.
In contrast to our hypothesis, this study found that the reliance on oxidative metabolism increased at maximal intensity. However, it is important to consider that maximal intensity was defined as work rate rather than VO2 max. The study found that PDH activity was not limited by oxidative metabolism. This study did disprove our hypothesis. However, based on the evidence we have looked at in class and the limitation we noticed in this study, we believe that our hypothesis has not been entirely disproven just by the results of one study. Because after all, physiology is not just black and white.